Hi there. Welcome to the IUR summer course titled An Introduction to Polynomial Optimization. So this is at Columbia University. So we'll start here with the first lecture titled Why Polynomial Optimization. And so I'll give you a short answer to that right away. So why study polynomial optimization? Well, polynomial optimization consists in minimizing a polynomial subject to polynomial inequalities. And this is actually a very general class of problems. And it includes special cases, probably things that you have seen in your courses. So linear programming is a special case. Then we have also quadratic programming, which is minimizing a quadratic function subject to linear constraints. Also a special case, integer programs, and also mixed integer linear programming. And then also more complicated things like quadratically constrained quadratic programming. So as you can see, a lot of problems in OR and operations research and industrial engineering, they fall into this framework. And why is it so interesting is polynomial optimization is at the heart of a revolution in the field of optimization that happened around the year 2000. And at that time, what happened is fruitful connections to mathematics were discovered. And in particular, measure theory, operator theory, and algebraic geometry. And so, the reason why I think it's an interesting subject is that, it's a new polynomial optimization is a new and active area of research. There have been some nice references now that have been written on the subject, and for this course, I would recommend these two. So an introduction to polynomial and sum-algebraic optimization. That is a very good, I think, way to start. And then if you want to delve more into the, more proofs, it's the other book on the right is a little bit more complete. I would recommend those. So a little bit about me. So who am I? So I'm an assistant professor at Columbia University in the IOR department since last summer. And my research area is broadly non-convex optimization. And my past teaching experience has been to teach like basic programming. I've taught analysis on Hilbert spaces, non-smooth convex optimization. I've also taught numerical optimization, theory and algorithms. I taught actually optimization models and methods last semester, and then I also teach a bit of dinghy sailing in the summer. So an outline for the summer course. So it's going to be 3 lectures. So lecture 1, which is this one, so why polynomial optimization. So I'll try to give you some motivation, some background, and then lecture 2. And lecture 2, we're going to focus on polynomials with one variable. That will be more simple. And then in the 3rd lecture, we'll look into multivariate polynomial optimization, which I guess is closer to applications where you can have a lot of variables. Okay, so we need to step back a little bit and consider consider the case, or consider convex optimization as kind of a backstory for this. So what do we mean by convex optimization? So we're minimizing a function f of x subject to some non-negativity or non-positivity constraints, gi of x. You have m constraints here. And x, your decision variable, is basically a vector of n real variables. Okay, and a convex optimization problem could look like the one you see there on the figure, where you have so f of x drawn in function of a single variable x. And the thing that's so what's nice about this framework is that we actually have highly efficient algorithms that can solve this class of problem. And so, and then just backtrack, just so to define more formally convexity, what it means is that when you have, if you take 2 points on the function and you take the segment that links them, then that segment should always be above the function. And so it has this nice curvature that you see there. And so in fact, this is the reason why you have very efficient algorithms. So if you, let's say you try to do an iterative approach, so you just take a random, first iterate, and like say x equal to -2.5, and then you just look in a neighborhood nearby for a better point. And if you do that, you could get this other iterate. And then if you keep doing that, you see that you nicely converge to the minimum of this function. And so the issue, the thing here, so this is very nice, but the thing is that many real-world problems are actually not convex, and so they actually look more like this. So this kind of function where, as you can see, the convex definition or the property is violated, because now if you take this segment here between 2 points, it's not always above the function. It actually is sometimes below, and so this actually causes this can if we do the approach that we just tried, which is just so what this yields these notions, one of local solution, so you're only the best solution but in a neighborhood, and this other notion of global solution, which means the best among all the decisions you can take. And so what happens is now when you do this approach of just taking iterates and looking in the neighborhood and trying to make it better, you could end up having something like this happen. And so you're going to converge towards a local solution. And so that is kind of the disadvantage here. So algorithms may fail to converge to the desired solution. But yeah, the nice thing here is at least now you can model a myriad of applications. And so now how does polynomial optimization fit in the picture? Well, basically it's non-convex optimization where we make a very mild assumption. We say that the objective function f of x and the constraints gi of x, we restrain them to be polynomial functions. As it turns out, this is like a very mild, there are many problems that are non-convex that are actually naturally written like that. And so what is nice is that now if we make this structural assumption, well, now we can actually solve this to global optimality. We can guarantee, we can avoid getting stuck in that local min as we just saw. So let me show you how like how one can do that. So what you can do is you can compute a sequence of converging lower bounds, as you see here. And what happens is that then at some point the bound will be tight and it'll touch the global solution. And so there's a systematic way to do that. The conditions for convergence are very mild. Actually, it's just really asking that your feasible set is bounded. And that is really something that, in general, in applications is reasonable to assume. But I guess to have the full picture here, the guess kind of a little bit drawback here is that computing these lower bounds is actually quite expensive, and so you got to be smart about how you do that. And so, in fact, it's possible, but you have to exploit the problem structure that you have in your problem. So it could be there's some kind of symmetry in your application, or it could be that your problem, maybe it's large scale, but it has a lot of sparsity. There are many terms that are actually zero. So you get this, as I was saying, you get the global solution. So let's see, speaking of applications, so how does polynomial optimization apply, for instance, to power systems? So here we're interested in minimizing generation costs subject to physical laws. So those are basically the Kirchhoff law and the Ohm law. And then we also have engineering constraints. The voltages have to lie within some, some margins for safety reasons. And the flow on the lines is also has some upper limits to avoid overheating. And so in these constraints, you actually have, when we use, most networks today are using alternating current, and that actually makes for a lot of non-convexity. Fortunately, as we'll see, it's actually not too hard to turn this into a polynomial optimization problem. We're going to see an example of that. But just for now, let's just say that already finding a feasible solution, something that would satisfy these physical laws and these engineering constraints on like a large scale, like the US grid, is actually already, it's already a challenging problem. And then finding a solution that would be like locally optimal with respect to, let's say, minimizing generation costs, that is already a little bit harder, but it's already a little bit better. And then ideally, you would want to find a global solution that satisfies all the constraints. And to give you an idea of the discrepancy between local and global, just bear in mind that this is a huge industry. So 2017, according to the Department of Energy, United States, you have $390 billion in sales revenue. And so if you can imagine just making 1% of savings, that's already $4 billion a year. So it's consequential. So let's actually apply now this polynomial optimization framework that we just mentioned to power system. Let's take this small example. So this is from the Midwestern United States. It's a little network where you have basically the bottom half of it is high voltage, very high voltage, and it has some, what you see, the G, those are generators, and then they're connected to this upper section of the network via these kind of teeth that you see there. And these are transformers, and they transform to a lower voltage. And so this might be a network where you have, like more power consumption, the households, and so on. And then all these arrows are they're connecting to other parts of the grid, essentially. And so we could write an underlying graph for this, for what we just saw, for the network that we just saw. And in fact, here you just have 14 nodes. And so each node corresponds to an electric bus, and then the edges correspond to the lines, physical lines. And so computing, what we're interested in is computing an optimal power flow. So I've computed it here actually on this problem. So you see the black nodes are, they're connected to a generator. And so we're trying to compute the power production to meet the power demand. And so the power production is in black. It's the black numbers that you see that are represented in megawatts. And then in red, that's the fixed power demand that you have to meet. And so you can see there's demand at all the nodes, with some nodes having zero demand. And so you see, and so the arrows are all the flows, the direction of the flows to meet that demand. So here you see a flow that's globally optimal, that minimizes the total power generation. Yeah, so I'm only showing you here the active power. There's also this notion of reactive power that is also being computed. I just didn't show it here. But this is highly linked to what I just said with alternating current being a part of our physical laws. And this is actually one of the main sources of non-convexity. And to give a little bit of an intuition, so when you consume, let's say you use your heater to heat your apartment, that is actually, so basically electric energy being converted into thermal energy, and that is going to consume active power. But if you're going to convert electric energy into mechanical energy, so say your tumbler in the washing machine or a metro, that is actually going to consume reactive power. So that's to give you a bit of the intuition behind those notions. So we actually have both, the demand is actually, we have both fixed active power demand and reactive power demand, and then we have to compute the generation, both active and reactive. And so it turns out that this problem of computing how much to produce and all the flows that you see, the arrows, is actually all comes down to just computing the voltages at each node. So each node has this notion of voltage, so here we really have these 14 different voltages that we want to compute. Once we have the voltages, then we can compute everything else. And so let me show you actually on a very simple example this 2-bus system. So on the left you see this power generator that generates so at the cost of $2 per megawatt hour, and it has to we have this fixed power demand on the other side, on the right side, so 350 megawatts, and then minus 350 megawatts. So that's the reactive power part that I was telling you about. And so we have to compute, so now back on the left, we have to compute the P gen 1 and Q gen 1. These are the active and reactive power that we need to compute. And as I said, you can actually view your variables as just being the voltages at those two buses. And so we have narrow, you see they need to be basically plus or minus 5% around this nominal value, which is called per unit, but basically just we can view them as being something that has to be around 1, the magnitude of these voltages. And so these voltages, so the optimization problem is we're trying to minimize this, the cost of producing the power, and we have to respect these these voltage margins, and then we also need to respect, so we have these power balance equations, the two at the end that you see. Okay, so I've actually written out for this system what the optimization problem looks like. And so you can actually identify real and imaginary parts. So if I just show that again, you can write V1 as essentially x1 being the real part, and then x3 being the imaginary part, and then you could do the same thing with V2. You could take x2 to be its real part, and then x4 to be its imaginary part. And so then this is what it looks like when you identify real and imaginary parts. And so now we have, as I promised, we have an optimization problem where the constraints and the objective are polynomials. So this is actually an instance of polynomial optimization. So as I said, polynomial optimization, not only it encompasses many classes of problem that you may have seen in class, but just naturally many applications such as this are just going to be written as polynomials. Okay, so now we can apply these ideas of computing these lower bounds, and then hopefully at some point computing the global solution. And so let's actually illustrate this on real-world data. Fortunately, we actually have access to data from 23 different European system operators. So they're available on MatPower, which is a package of MATLAB. And so you have all these interconnections, all the data for all the lines that you see there that are available. And so here we can, I'm just going to show you here some of the numerical results when you apply this. So this idea of, as I said, converging lower bounds, there's actually a more precise kind of approach, which is called Lasserre hierarchy, which computes these lower bounds. And in fact, here we're able to compute in each instance. So we're able to compute the global value. So it's actually finding a lower bound, but it's actually tight. It's touching the global solution. So you see on the left here, you have a bunch of different test cases. These are a bunch of benchmarks. Some of them come from the US grid, and others come from the European grid, as I just showed you. The PL is for Polish, and Big As is like a a bunch of different countries, mostly in Western Europe. Yeah, and so here what I'm showing you in the middle column is the global minimum. This is the best that you can do when you try to minimize. Either it's you're minimizing the total power production, so then it's going to be in megawatts, what you're seeing the number, or it's going to be in dollars per mega per hour. It's some other notion. And so those are the best that you can do. Try to optimize over these benchmarks. And so this was done using the LSA hierarchy, and you can see that the runtime is encouraging because it basically is about the order of a few minutes. You're able to compute a global solution. And just in case you're not familiar, like finding a global solution to a non-convex problem is an NP hard problem. It's a very hard problem. And doing it on a large scale is really not it's tricky business. And so to give you an idea here, basically these are instances of quadratically constrained quadratic optimization problems with up to 4,000 variables and 20,000 constraints. So to give you an example, this is what you would get if you compute these optimal power flows on a large grid. And so what's very neat, I think, is that this reflects the reality of the energy flows in the grid. And so you can see here, for instance, so Italy, for instance, is mostly an importer, net importer of electricity. And you can kind of make a bit of sense of that, given that, for instance, Italy didn't invest. So in the 80s, several countries in Europe heavily invested in nuclear. Italy did not, and so you can see just there's a bit of discrepancy here. France is exporting quite a bit. There's a lot of trade between France and Germany. These are like key players on this market. And what's interesting is that you don't really control. So just much like thunder just follows the most conductive path. And this is exactly what happens in the electric grid. Is so if France wants to trade with Germany, it doesn't get to choose where that trade is going to happen. You see that there's a bit of trade between France and Germany, but in fact there's direct trade. But there's also a bunch of trade that is actually going through other countries, such as Belgium and the Netherlands, Switzerland. And so this brings all like these very interesting kind of engineering problems where these countries where power goes through, they need to use like transformers, and they need to make sure that their grid can sustain these heavy flows that basically cross their nation. So yeah, I think it's very exciting to be able to test these methods on real-world data. So now I'd like to just get a little bit more into our hands into the actual kind of framework that we're looking at. So we're trying to minimize polynomials, as I said. So polynomial in the multivariate case, so it's the sum of basically a coefficient times a monomial. And a monomial, like x to the power alpha, is basically just x1 to the power alpha 1, which is an integer, like 1, 2, 3, it could be 0 too, all the way to xn times alpha n. Okay, and this is subject to polynomial inequalities. And usually with polynomials, it's common to write it as non-negativity constraints. And the same thing here. We have the GI are the sum of coefficients times these monomials, x alpha. Okay, and yeah, what's nice is that this is a very general. As I said, it includes many special cases, many widely studied problems of special cases, and it generalizes a lot of the theory that you might know about these. Like for instance, integer optimization. If you know of like Sher-Ali Adams, basically Lasserre or this whole framework allows you to generalize into kind of. It gives you a better understanding of what those methods really do. So yeah, a lot of OR problems. Just want to note, why does it include integer programs? It's very simple, because if you have like a binary variable that x is only equal to 1 or 0, well, you can easily model that using polynomial. You just write it as x times 1 minus x, only solutions being 0 and 1. And then also to get a sense of how broad really this is, this class, just think that polynomials can approximate any continuous function as closely as desired, um, on bounded sets. But so effectively, you can really model a lot of problems with this to basically arbitrary accuracy. Yeah, so as I just to repeat a bit, but you have a global convergence guarantee, and this is under a very mild assumption, and it's basically that the feasible set, so defined by the polynomial inequalities gi of x, and that's the feasible set is bounded. Now, of course, just to recall, like if you have, you can also have equalities, and you just have to write gi and then minus gi, and if both of those have to be non-negative, then it's actually equal to 0. Okay, and so now I'd like to finish this lecture by giving you a graphical intuition of how this how one can solve these polynomial optimization problems. Like why is this algebraic assumption that we're making, why does it somehow help us? Like in practice, what can we do with this? And so for that, I'm going to borrow, and I thank Marcus for allowing me to do so. I'm going to borrow some slides. Marcus Schweighofer, who's a professor at Constance University, and I think there is really no better introduction to the topic. I wouldn't be able to do a better one myself, so I figured I'd just show you this. So notice how you can really model very diverse geometric objects using just polynomials. So right here, you have 3 variables, one equation and one inequality, and you can see like the high level of non-convexity you can model using that. Another really beautiful example is this one here. You have this equation, 4th degree, and then the ball, and yeah, you can see you can have all kinds of singularities, and it really models a lot of things. Another example, yeah, this is really beautiful. You gotta watch, admire this. Thank you again, Marcus. And so let's think about how, so here's an example of a polynomial optimization problem. And so here you have 3 variables. And so you're minimizing this objective, x1 times x2 squared plus x1 times x2 times x3 to the power 5 minus this other monomial times 3 plus 7. And you have these 4 variables, and you have these 4 polynomial inequalities. So one thing that you can do, just very naively, that is tempting to do, is you could try to get rid of non-convexity. So the non-convexity comes when you're multiplying these variables with one another. So all these monomials, basically, they lead to non-convexity. So what you could do is you could just, as a first approach, you could just basically replace these monomials by new variables. So for instance, so here we have x1 times x2 squared that shows up in 2 places, so we could replace it by a new variable, let's say y1, okay? And we could just, pick another monomial. You have x1 times x2, and then you replace that by another variable, y2. And you just keep going, whenever, so x2 squared, you could replace that by y3, and then we have this monomial, replace it by a new variable, and so on, to y6, y7, y8, 9, 10, 11, 12. And now we have no more monomials. So we have, or we don't have any more products of variables. We still have x1, x3. We still have the variables, the original variables. Some of them are still in the problem, but now we have all these other new variables. So we have these new variables y, and so what we effectively did here is that we started in 4 dimensions, and then what we did, that was non-convex, and what we did is we added new variables, and we added enough so as to make our problem convex, in fact, linear. Now it's a linear program. And so you can try to solve that. And so you can kind of see that now you're going to find a lower bound to your original problem, because whatever you're doing now is just weaker. It's less constrained. It's relaxed compared to your original problem. But so this is a bit naive. So obviously you can't expect that this will allow you to solve your problem. It's probably going to find a bound that's really, really very low. Maybe even it could be minus infinity really. So it could give you something trivial. And so you could try to do something a little bit less naive. And so let's go back to our original polynomial optimization problem. And so remember, we have these 4 real variables that we're optimizing over, and then we can label our 4 polynomial inequalities. So we have A, B, D, and E. And what we could try to do is we could multiply, for instance, A times B. So both of them are non-negative, so if you multiply them, then they should also be non-negative. So you could, it's like redundant. You could add that as a constraint to your problem. It's not going to change anything. You could do the same, for instance, take a constraint and put it squared. I guess I don't know where C is, but it's one of the constraints there that you just take the square of it. I mean, it doesn't. If you have a square, it has to be non-negative. So, and then you could also take a square and multiply it by another constraint. That is also going to be non-negative. You could take 3, multiply them. That's non-negative. Okay, and you could do that. Let's say we stop here, and then now we could do the same procedure. So we try to basically take out all the non-convexity that comes from the product of variables, and so basically whenever we see one of those monomials, we replace it. So for instance here, x1 times x2 squared, we can replace it by y1, x1 times x2, can replace it by y2, and see, notice here how compared to what we were previously doing, now y2 actually shows up in several different places. Y2 only showed up before, it was only showing up in one constraint. But you see that now, because of those new redundant constraints, it actually shows up there as well. Just like the y1, the first one that we replaced, is actually, it used to only show up in the objective, but now it actually shows up in these redundant constraints that we're linearizing. And so that gives you kind of an intuition that, oh, we're going to have more, we're going to somehow constrain more those lifted variables y. And so in fact what we're doing is we're going to have more information about them at the end of the procedure. So if we just keep doing this, we replace this by y4, y5, we replace all these monomials by these lifted variables, and so we're going to end up again with a linear program. Okay, and now this linear program has actually more variables, so it has the 4 original variables plus 20 new lifted variables, and we also have more inequalities. But as you can kind of guess, like this is actually going to be better. It's going to give you kind of a better lower bound to your original problem, and this is this you can solve using linear programming. You can find this in polynomial time, the solution to this relaxation. And so yeah, this is what is being said here in French, is that so while those constraints, the blue ones, they were redundant in the non-convex formulation, they say they were useless, but they were valid, they were true. But now when we've linearized, after linearizing, they actually become really useful. They're not just redundant, they bring information to our lifted problem. And so this is kind of the general philosophy, is that you have a problem in like low dimension, let's say dimension whatever 4, you have some problem in some fixed dimension, it's non-convex, so to try to be able to find the global solution, That was a close call. And so to find the global solution, basically we embed our problem in a higher dimensional space. And that is kind of the main idea of polynomial optimization techniques. So let's try to have a more kind of graphical. Let's try to illustrate this in a graphical way, geometrical way, what I just said. So consider this system of polynomial inequalities. So equation A so corresponds to this blue region. Equation B corresponds to the red dotted region, and then we have the last one, which is this ball. Well, it's not exactly a ball, but anyway. So you can see that this set is non-convex, actually disconnected, the intersection of the three. And so an object that is going to become of interest is the convex hull of it. So various definitions, the intersection of all the convex supersets is one of them. And so to give an idea of what's going on here, what we're going to do to deal with these this system of constraints, we're going to lift our problem, as you see here, by adding these variables y. And what we're going to get, so let's do this linearization. So take the monomial x1 to the power of 3, replace it by y1, x2 to the power of 4, replace it by y2, and so on, and we just linearize the problem. And so now we have this y, these y variables, and we have a linear, so it makes for a linear inequality. So let's try to see, here it's a little bit too weak, so let's do, let's actually try and add first redundant constraints. So let's multiply basically the first and the second, the first and the third, and then multiply all of them together, and take the squared. Okay, and then now let's do this linearization trick. So let's replace all the monomials by these new lifted variables. Okay. Okay, and so what happens now, so just you can see here, you have linear inequalities where you have your original variables, x1 and x2, and then you have these lifted variables, y. And so what happens is that this is actually in higher dimension. This makes for a polyhedral set. And so you can see here on the picture, you can see the original feasible set, the non-convex black region, disconnected non-convex black region. That was our original thing that we had to deal with, where local optimization methods or traditional optimization methods would not be able to solve them with guarantee. In particular, if you have a disconnected region, it could potentially just get stuck in one of the regions. Maybe the global solution is in the other region. And so what you see here is that we lift the problem into this higher dimension. Now we have this convex region. And what you can see is that if you project it down to the original domain, it's going to be an outer approximation, or it's more of a superset of the convex hull. So it's not really approximate. It's guaranteed to contain essentially the convex hull. And what happens is that if we did this enough, these redundant constraints, and then linearize, if we propose enough redundant constraints in a sort of systematic way, then we would actually perfectly match, we'd be able to match the convex hull. Another thing that I think is interesting here is that now when we optimize over the polyhedral set, you can see like some of those corner points, when you're going to project them they are going to be actually not just in the convex hull, but you can actually get them to be in the black region, which means you can actually find the global solution. And so I think that's what's kind of impressive about these approaches. It's a little bit more than just finding, these convex kind of outer approximations, but it's also that this idea of being in higher dimensions, if you do it in a systematic way, you can actually kind of pinpoint your global solution, and then you can actually extract it from your higher dimensional convex problem. So this is actually all these things that we're going to see in lectures 2 and 3. I hope that you enjoyed these images because it's going to get a little bit more mathematical, but I promise I try to also keep it very, I do have images in the next lectures, and also it's going to be very example based, so you should have some kind of intuition for what is going on. Yeah, thank you for your attention, and yeah, I hope I hope you'll be following, or you'll be watching the next lectures. Thank you so much.